Hi everybody. Today we're going to talk about evolution in time and space. Until now we've been studying models that evolve in time. We've treated the temperature of the Earth as a single variable that changes over time due to different physical effects. But now what we would like to do is realize that actually the temperature of the Earth is not a single number. The temperature depends on where you are in space, where you are on the surface of the Earth. So today we'll look at how to model that in one dimension. We're going to look at two effects, advection and diffusion, that determine how temperature changes in time and space. So we will think of the temperature, capital T, as a function of two independent variables now, t and x. Little t is time and little x is space. And so we want to calculate a value of the temperature T at each point t and x. So for all time and for all points x in some region. So we'll take the region as being from 0 to some capital L. And we'll think about this as a channel with fluid in. So a fluid is flowing along a channel between position 0 and position L, or L sub x. And so we are going to start off with some initial temperature distribution or temperature profile, which we'll call capital T0 of x. But we actually need to represent that function, that continuous function, on a computer. So we need to discretize T0 of x in some way. What do we mean by that? We mean, well, we need to approximate the continuous function T0 by a finite set of numbers to be able to store it on the computer. So the simplest discretization method, but far from the only one, is to sample the function at discrete grid points or nodes x sub I. So we'll take n, capital N nodes, or capital N sub x, and for simplicity we'll take them equally spaced so that the distance between two neighboring nodes is a quantity we'll call delta x, which is just given by dividing the length of the system by the number of nodes. Throughout this notebook, we're going to use a temperature profile given by a sine wave. Let's define the grid points as we said just now. But there's a small wrinkle. Let's look at a picture of this. So here's my sine wave in blue, this blue continuous curve. And I've chosen some number of grid points, which are these green dots on the y-axis. And so at each of those points, I'm sampling the function. In other words, I'm just evaluating the function at that point. And that gives me this sequence of points that approximate the curve. A useful way to think about this is actually as follows. What we're doing is dividing the interval between 0 and L, and I'm taking capital L to be 1 through this notebook. We're dividing that into n cells. And actually the grid points we're going to place at the center of the cells. And the value that we're sampling at each grid point, we're going to think of as representing some kind of average value of the function spread over that cell. This is actually a useful way to think about these values in the context of the algorithms that we're going to implement. Okay, so let's turn to our first algorithm. So let's think about advection. What is that? We're thinking about a fluid. The fluid is moving along. And when the fluid moves, it will take with it anything that's dissolved, any contaminant, for example, that's dissolved in the fluid, or in fact, the temperature of the fluid. So if the fluid has different temperatures in different parts of the fluid, when the fluid moves along, the temperature profile will also have to move along just because it's being carried by the fluid. And any quantity that is carried along by the fluid in that way, we call a tracer. So let's fix our attention at a single grid point xi. What will happen to the temperature at that point? Well, it will change over time. And it will change over time because fluid is moving along, and so the way it will change over time is actually influenced by the value of the temperature at neighboring grid points, because heat will be transported from a neighboring cell into the current cell. So what we need to calculate is how much heat will move around during this process. So let's call delta t the duration of a time step. So we're going to do a time stepping algorithm just like we've done in various other parts of the course. So we're going to move along by time steps of length delta t. At each time step, we will update all the variables to model the physical process. So let's denote by capital T superscript n subscript I the approximate value of the temperature at time step number n and at the grid point number I. This is what we need to calculate with our algorithm for each n and I. So this is the discrete approximation of the temperature field. And just a remark that n here is not a power, it just denotes a label labeling the nth time step. So for example, what is capital T subscript I superscript n plus 1? Well, it's an approximation of capital T at the time Tn, the nth time step, plus delta t, because it's the next time step, so we added a delta t. And so you can see that it might be useful to expand this expression in a series of powers of delta t using a Taylor expansion. And we'll use that later when we derive equations describing this process. So now suppose that the fluid is moving to the right with some speed capital U. What happens during a time step of duration delta t is that some heat leaves the cell. But a lot of the fluid, if the time step is short enough, a lot of the fluid inside that particular cell, it's moving to the right, but it will stay within the same cell. And so we have to calculate how much of the fluid will leave the cell. So the amount that will leave has to lie within a distance capital U times delta t from the boundary of the cell. And any fluid within that distance will manage to cross over the boundary and move into the next cell. So a proportion U delta t divided by delta x, which is the width of the cell, is how much crosses the boundary. And so we take the total amount and multiply it by that proportion to give the amount of heat that will cross the cell boundary. And similarly, from the left cell, from the cell to the left of cell number I, a similar amount, but now with the quantity Tn I minus 1, will cross into cell I. So what we're going to do is a sort of gain and loss calculation. We're going to say that the quantity at the next time step in cell I, Tn plus 1i, is the quantity that there is at time n plus what I gained from the left-hand cell minus what I lost from my current cell. And so this gives an equation describing the discrete time evolution of my system at each time n and each cell I. We can rearrange that formula in this way. You'll notice that, well, now we have expressions which look very much like derivatives. And so when we take a suitable limit, when delta t and delta x go to 0 in a suitable way, we actually arrive at a differential equation because these are derivatives on both sides. But they are derivatives with respect to different variables, with respect to time on the left and with respect to space on the right. And so what we get is this equation with two different types of partial derivative of this function with two variables. And this is a partial differential equation. So this partial differential equation is called the advection equation, and it describes this motion of a tracer that's being carried with the fluid, which is the process that we call advection. Partial differential equations, or PDEs, sometimes have analytical solutions, and that is the case for this equation. But we're interested in how we can solve this numerically. Usually when you have a partial differential equation, what you need to do is discretize that equation and solve it on some kind of discrete grid. Actually, we already arrived at one particular numerical method, which was this one, which tells me the time evolution. On the left-hand side, I have the value at cell number I at time n plus 1, and on the right-hand side, I have information that's only at time n. And so I can just step forward in time. This is basically the Euler method again that we've seen for ordinary differential equations. And so I can just transcribe this directly into Julia code. So I'm calling capital T in Julia will be the current values of the temperature at all the grid points. And then T prime will be the new values at the next time step. But if we look at this code, we realize that there's a problem. We need to calculate these new values for each cell number I. But what happens if we set I equals 1? Then we're actually trying to access the element number 0 of the array. In other words, we're trying to access an element of the array which is outside where the array lives. The array in Julia is indexed from 1 to n, and we're trying to access element number 0. And so this highlights the fact that a partial differential equation needs not only an initial condition, but also boundary conditions that tell us what happens literally at the boundaries of the domain. So there are various different kinds of boundary conditions that we're talking about in another video, but we're going to choose periodic boundary conditions. So this is a convenient mathematical fiction where we say, well, let's wrap around the system into a sort of torus so that the point on the left of the system is touching the point on the far right of the system in this kind of donut shape. And that enables us to treat all of the cells in somehow in the same way, with having the same number of neighbors. There are various ways in which we could implement these periodic boundaries, but I've chosen a simple one. Here is again the same piece of code now in an actual Julia function. So we're passing in a vector of the current temperatures. We make a new empty vector with the same length called t prime, and then I loop over the bulk of the system. That's the interior cells where I don't need to access the boundary elements. So you see that I'm starting with I equals 2, and so this I minus 1 index is always going to be inside the array. But then I have to separately treat the boundary cells. So I have a separate equation that's just valid when I equals 1. When I need to access I minus 1 for I equal to 1, well, instead of 0, I'm going to put capital N. So that's the end cell of the array. That's saying that the left-hand neighbor of cell number 1 is cell number N. And that's a way to implement these periodic boundaries. So we've also written a function evolve that just carries out a generic time evolution where you tell it which function you want to iterate, and it iterates it for a certain length of time. And that, as I said, this is basically the Euler method now applied to this vector of values all at once to give us the new vector of values tn plus 1 at the next time step. So let's fix the time step delta t and the speed u and evolve our system from this initial condition that we started with using advection, using those parameters. And what we get is this result. Here's the initial condition at t equals 0 is our sine wave. And I'm going to evolve the system, and you can see that the speed is very slow, so it gradually moves along. Let's speed it up a bit. It moves along at some speed. The profile is moving along as we expect that it should. However, it's also, unfortunately, doing something else, which is decaying over time. The amplitude of this profile is decaying, which we were not expecting. And so it turns out that this particular numerical method is actually not very good for simulating this system. This is called an upwind discretization of the differential equation. And despite the fact that we derived it from these physical considerations, there's actually numerical dissipation or numerical diffusion. So we'll look at diffusion later in the lecture. But for now, let's try and use a better algorithm. If we think about this spatial derivative d by dx that occurs in the differential equation, it turns out that we can actually discretize it in a more accurate way using this so-called centered difference. So you see that instead of the difference between the temperature at cell I plus 1 and the temperature at cell I now have the difference between temperatures in cells that are spaced 2 cells apart. And this gives a more accurate approximation of the partial derivative. Okay, so we can implement that just by replacing the expression that we had by this new expression for the derivative. But now we actually need 2 periodic boundary cells at both ends of the system. And we need to be careful to implement that correctly using the correct boundaries. So again, the left-hand neighbor of cell 1 is cell n, and the right-hand neighbor of cell n is cell 1. Okay, so I called that advection 2. And so when we evolve using advection 2 instead, what do we find? We find that now the system actually behaves as we expected, as we hoped. Basically, it's moving along, this profile is moving along at a certain speed, and it's pretty much maintaining its shape. So let's try just checking, is it doing the correct thing? The speed that I used was 0.2, so we expect that in a time 1, the profile should have shifted along, should have moved along a distance 0.2. So let's check that. The peak of the profile starts at 0.25 at t equals 0. By t equals 1.0, well, it arrived actually at 0.45. So it did move a distance 0.2. So this is actually approximating the solution of this differential equation pretty accurately, where the profile moves along at speed u. So this is a reasonably accurate way to simulate this time evolution, provided we're taking quite small time steps. Now let's look at another physical process. There's another video about this as well, which is diffusion. And so let's remind ourselves that this process models how temperature spreads out from a hot region to a cold region. Or if we have some substance dissolved, for example, in water, it tells us how the concentration of that substance spreads out from regions of high concentration to low concentration. And basically, these physical processes are occurring due to random motion of the molecules that make up the system. That random motion results in this effective spreading out process. And that's described by this partial differential equation. So the partial derivative of the temperature with respect to time is some constant times the second derivative with respect to space. And this is called the heat equation or diffusion equation. And again, we can derive this from a similar kind of consideration of how much material moves from one cell to each neighboring cell. Or we can think about it as discretizing this second derivative, and it turns out that the way to discretize a second derivative, or one way to discretize it, is as this 3-point formula where we have t at position I plus 1 plus t at position I minus 1 minus twice t at position I. And we have to divide all of that by delta x squared. And that gives us an approximation of the second derivative at this grid point ni. So again, we can write that directly into Julia, taking into account the boundary conditions in the same way, and we'll call that diffusion. And now we can evolve diffusion in the same way. And what do we see? So I've used a small diffusion coefficient, and what we see is that this profile spreads out over time. So to understand a bit better what's going on, let's look at a different initial condition where we just have a peak. So we have basically a high temperature in the center of the system and zero temperature elsewhere in the system. And let's solve that using diffusion. What we see is that the profile gradually decays in the center and gradually spreads out through the system. This spreading out process is this diffusion. And finally, we can combine both advection and diffusion. This is basically a composition of functions of the advection and diffusion operators. And what we see is that the profile moves along and decays. So it's this combination of these two effects. Actually, just like we had using the very first algorithm, since that actually has an effective diffusion built into the method, it turns out. We've seen that diffusion and advection are two physical processes that can occur in a system that evolves in time and space. And in the next lecture, we'll see how we can extend those to 2 dimensions. See you next time.